In this video on section 7.4 of chapter 7, we're going to develop formulas for integrating and differentiating inverse trigonometric functions. We're going to start with developing a formula for the derivative of the inverse sine function. So let's start with the function y equals sine inverse of x, and we're going to try and figure out a way to differentiate that. The way we're going to do that is to take the sine of both sides of this equation. So the sine of y then equals the sine of the sine inverse of x, the left side. Left side doesn't change any. The right side, when we take the composite of a function and its inverse, remember we just get the x, and so we're going to write this as x equals sine y by flipping the two sides of the equation. So what we've done is we've converted from y equals this to this alternate form for the inverse sine function x equals sine y. Now we're going to use a formula in the book for differentiating functions of x that is found on page 152 in your book, and it says that dy dx is equal to 1 over dx dy. I mean, if derivatives were just fractions, that would be obvious. We actually have to go through a proof of that, which you see in that blue box on page 152 of your text called a deeper look, which shows how to derive this formula. So we're going to apply this formula so that we can take the derivative of this function with respect to of this x function with respect to y. So we're going to take dx dy, which is going to be the derivative with respect to y of sine of y. So let's pick that up on the next blackboard. So dx dy is the derivative with respect to y of sine y, which is cosine y. And now we have to figure out what cosine y means. Remember that when we went back to the original, y would equal sine inverse of x. So what we really have here is cosine of sine inverse of x. So let's draw a triangle to help us out here. And on this triangle, we're going to have y, we're going to set y equal to sine inverse of x and call that also theta, the angle in the triangle. Now we're going to take the sine of both sides, so we get sine of theta equals x, which equals x over 1, which for a coming from the definition of the sine function, that is the opposite over the hypotenuse for this triangle with theta positioned here. And so the opposite we've got as x, and we're going to put the hypotenuse as 1, and that makes this bottom side of the triangle here by the Pythagorean theorem 1 minus x squared. So if we go back to our derivation where we left off right here, we've got the cosine of sine inverse of x, which is the cosine of theta, and the cosine of theta is going to be the adjacent over the hypotenuse for this triangle, so the adjacent over the hypotenuse. And what is that going to be? The adjacent is, we just figured it out, square root of 1 minus x squared, and the hypotenuse is 1. So the dx dy is this. Now remember what we were trying to find, though. If we go back to our original slide, we were trying to find dy dx, and since we weren't able to do that directly, we were instead going to find it as the reciprocal of dx dy. So we just found dx dy, and so now we know that dy dx equals the reciprocal of dx dy, or since we know this, and we just found that dx dy is this, and so we have what we need. So y, remember, was sine inverse of x, so we'll plug that back in. Derivative of sine inverse of x is 1 over the square root of 1 minus x squared. So we found the derivative of sine inverse of x. Kind of a surprising answer, certainly not what we would expect. This, if we convert this formula into its integral form, we're going to integrate the left and integrate the right. We get this this formula. So we're integrating the left side, which is the derivative of sine inverse of x, and we're integrating the right side, which is this fraction. And when we integrate the derivative, we just get sine inverse of x. So if we collect that together into a formula, we get dx over sine inverse, over 1 minus x squared is sine inverse of x plus c. So here's a fairly important integral formula. We'll learn another way to come up with this formula in Chapter 8, but when we have this kind of a structure, a square root in the denominator that has the form 1 minus x squared, we can integrate it and we get sine inverse of x. I'm going to put up a picture here that gives us a little bit more information about the sine inverse function. So here is the sine function in green here, and here is the inverse of the sine function, and you can see that there are reflections of each other about the line y equals x, this line right here, and you can see some derivative information on here. But the most important thing from this derivative formula is that we can write it in this integral form here. So let's do something similar and derive a formula for the derivative of the inverse tangent function and convert that into an integral form. So now if we continue as on page 153 of your textbook, and we let y equal tangent inverse of x, we take the tangent of both sides of that and get x equals tangent y. We use that same formula that we had from before, that dy dx is 1 over dx dy, and so we're going to find dx dy, and then our dy dx that we want to find is just going to be the reciprocal of that. So dx dy is dy of tangent y, which is the derivative of tangent is secant squared y, and that is secant squared of tangent inverse of x, because that's what y is. Then we have to set up the triangle as we did before with the angle in it, theta, equaling this time the tangent inverse of x. So tangent of theta equals x, and tangent of theta is the opposite over the adjacent. So if we fill that in, the opposite is x, the adjacent is 1, and this side of the triangle by the Pythagorean theorem would be 1 plus x squared. And so if we continue our derivation, we wanted secant squared of tangent inverse of x, which is the same as secant squared of theta, which is secant of theta squared, and secant is what, is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so this is the hypotenuse over the adjacent squared that we're trying to find. And so the hypotenuse is this, and the adjacent is 1, and we're squaring that, so we get 1 plus x squared is what dx dy is. We were trying to find dy dx, so we use again that dy dx is the reciprocal of what we just found, dx dy, so it's the reciprocal of this, and so the derivative of y, with y being tangent inverse of x, is the reciprocal of what we found for this. And if we put that into its integral form, we get this, that the integral of dx over the quantity 1 plus x squared is tangent inverse of x plus c. This integral formula here turns out to be very, come up quite a bit in application problems, and so let's do an example with it. So in doing this, we notice that if we let u equal sine x, then this integral is in the du over 1 plus u form, so u is sine x, du is cosine x dx, and so this top is du, and this bottom is 1 plus u squared. So we then have what converted it to the integral du over 1 plus u squared, which is tangent inverse of u plus c, which is tangent inverse of u being sine x plus c. So notice that there are problems in the text on page 158 where you would use this same formula, 1 over 1 plus 4 x squared dx. If you rewrite that as rewrite that denominator as 1 plus 2x quantity squared, and then let u equal 2x, then you can do this problem using the tan inverse integral formula, this formula here. And there are obviously lots of other examples. We'll be looking at a number of more examples of these two integral formulas, this one here and this first one that we developed here in the homework exercises. So this will conclude this video on section 7.4 with a final note that on the test I would want you to be able to do these two derivations. How do we find the derivative of the sine inverse function, and how do we find the derivative of the tangent inverse function, as well as how do we apply these formulas. So that's the end of this video on section 7.4.